very much. I think it goes without saying that I'm extremely happy to be back here with all of you this year. We're going to go off the rails a little bit in this presentation, so I hope you enjoy that. So let's go ahead and get started. Before the seas in this terrestrial ball, the heaven's high canopy that covers all, one was the face of nature, if a face, rather a rude and indigested mass, a lifeless lump unfashioned and unframed, of jarring seeds and justly chaos named. So this is from the Metamorphosis, written 1st century AD. And for thousands of years in our culture, we've had this juxtaposition of order and chaos. Chaos is what existed before the creation. And order is what was brought by a god or gods into the world. And for these thousands of years, it's been largely the role of artists to maintain order in the face of nature. Nature, the chaos, nature, the destructive. Artists producing, architects producing things of great structure, order, and rational behavior. We have this Newtonian worldview that existed up until the early part of the 20th century. So things like quantum mechanics, things like thermodynamics becoming prevalent, things like the chaos of World War I, causing sort of destruction that's beyond rational understanding, led to this shift in art. And so I've been working with chance operations, chaos, randomness in my work now for over a decade. And it's really only been the last year that I've started to look at it and to try and analyze it and come to terms with why I'm using it and how I'm using it and sort of where that comes from. And so this talk, in a way, is this journey that I've had over the last year in trying to sort this through. And so we're going to start with looking at a catalog of work and then proceed forward from there. So these are the very first things that I programmed. They're from around 1998. And when I first started making things in code, these were small interactive pieces. Every line of code was precisely determined by myself, and it produced something exactly as I wanted it to be. This was the piece that came after that. And then this kind of work studying time and motion, but also with really precise determined geometry. It was at that time that I became obsessed with artificial life and artificial intelligence and the phenomenon of emergence. And so these are the very first things that I made where I was not in entire or total control over the images that were coming out. It's an enlargement of one of those. This is the second step there. It merged into this. This is a detail of that. And then I took out all the color just so the structure remains and I could really look at that in isolation. This is an image of an actual print, so you can see some of the quality of the physical object. I started working on a new set of algorithms that I was inventing from scratch this time, rather than building on top of existing ideas. This found its way into an installation where instead of seeing something in two-dimensional on the wall or on a screen, you're able to move around. This one's highly animated. Everything's flowing from the middle, decaying towards the edges. And a goal of a lot of this work was to try and make things that were artificial that still had an organic quality too, and to try and split the difference between. This is a performance for Steve Reich's Music for 18 Musicians using the same core algorithm. And so after about 3 or 4 years of working in that way, I decided to make it very concrete. I became highly influenced by a lot of artists working with text, especially from the 1960s, kind of people under the loose banner of conceptual art. And so the system that I defined sort of after I started making the work, you had a few different forms, a circle and a line. You had these behaviors. And then you combined them together into elements. And these core elements then became the fundamental component of these systems that are producing these images. So about 1.5 years ago, I wrapped up that exploration with this series of 15 images, process 4 through 18. And we'll just flip through those so you can get a sense of the different sort of visual qualities that emerge from this small set of instructions played out. So working on finding the most minimal structures, these really simple clockworks that then produce something that have a surprising visual quality in relation to the simplicity of the systems. This was how this work was finally installed, basically a little bit of a family tree of the different processes. And let's look at one in a little bit more detail. This is element 5, which is the basis of a few of the processes. So we have a line that moves on a straight line, enters from the opposite edge after moving off the surface. It orients toward the direction of the element that it's touching, and it deviates from the current direction. So you can see everything is ordered, everything is precise geometry. We have a line that's moving straight, but then we have this last behavior here, 7, deviate from the current direction. And so the question is, what does that add to it? What does that cause to happen? So if we look at process 18, which is basically a description of how element 5 is imaged, we see a rectangular surface filled with instances of element 5, each with a different size and gray value. Draw a quadrilateral connecting the endpoints of each pair of elements that are touching. Increase the opacity of the quadrilateral while the elements are touching and decrease while they are not. And so when this work is installed, you have the instructions of the process here, the instructions displayed. This is the element, the diagram of the element, and then the element is defined here. So let's look at this as software. So what you can see is the ratio or the relationship here of the order to the noise being added to it. And what I found over time is if these lines don't have any bit of noise or jitter, they gradually tend towards one location. The system becomes homogeneous. They all group together, move in the same direction, and then it becomes basically unified. And so in a lot of the work what I'm trying to do are to make these systems that are continuous. And 3 days later, they have the same texture or the same general quality, but the elements shift and move around. It's more about the massing and the changes. And so the way to read this is to look for a grouping of lines and then look to the other side and see how those are drawing into the surface. So in this case, adding this slight bit of noise keeps it something that's more homeostatic and doesn't tend towards order. These are a series of prints derived from process 18. As things shift to print from software, their visual quality changes. There's more resolution in time and space. A series of milled objects, again, from process 18. And these are a set of colored prints from process 18. Another project, this one's a collaboration with Ben Fry. This one's called Signals. And it is a visualization of biology data. So we worked with a lab at MIT. And what you're looking at is the way that proteins communicate back and forth positive or negative signals within a cancer cell. And so here, everything is structured and ordered. I guess if you could assume the data is structured and ordered, which we did. And randomness is used slightly in order to determine the position and the scale of these individual clusters. And it reads from left to right based on time steps. I want to talk about this work in a little more detail. This is the tissue work, as it's called. This is a large print of tissue that's currently up at the Art Institute in Chicago. This is another view of the same piece. So when I started this work about a decade ago, it was based on this book, really elegant book written by a gentleman named Valentino Breitenberg, who's a neuroanatomist. And in this book, he describes a series of hypothetical vehicles based on his understanding of how nervous systems work across the animal kingdom. And so the way to read the diagram is this is something that senses something, and this is something that propels or actuates. And you can have these different physical connections, straight-through connections, cross connections, and a bit of both, which is more of how it actually works in biology. This mimics how our eyes map to the other half of the hemisphere of our brains. And then when you put these in an environment, and for example, if this is tuned to something in the environment, this simple wiring, this shift in the physical properties actually creates the behavior. So if it's a straight-through connection, it approaches and then stops. If it's a cross connection, it approaches and then veers off as one of these receives more stimulation and then causes whatever is moving it to move a little bit faster. Breitenberg kept it really basic, really abstract. And so the first thing I did was to try and build a simulation of these conceptual vehicles in software. And that's what we're going to look at now, briefly. So the way to read these diagrams are that each vehicle is clear. The gray dots are what they're interested in, according to the simulation. And then the color coding is based on the wiring that they have. Do they have an inverse or a positive relationship? Do they have a straight-through connection or a cross connection? And so it gets more interesting when you add more into the space. And they start off with an even distribution, sort of maximum entropy. And over time, order begins to emerge as they follow their behaviors. And as you might guess, the ones that have the same wiring, the same sort of physical behaviors, begin to group together and the structures formed. And as I was working on this, I became far more interested in the paths that they were taking while they were moving, far more so than the individual location at any given time. And what happens is over time, they move into this area where they cycle through, but in constant dynamic motion. And if you move one of these elements just a slight bit, things need to restructure and reorder. So there's a lot of order in here, but a little bit of chance, kind of in the same way we saw before, that they need to jitter just a little bit, to have a little bit of imprecision in order to not group together. For example, this would be just a perfect circle if they weren't made a little bit imprecise, and it have a little bit of parameterized change. So again, this is a print that derived from that, and this is a series of dresses that I collaborated with my wife on, using the tissue images in relationship to the geometry of the body. This is another project called Chronograph that I built with a collaborator named Tal Rosner. And this is a commission for a Frank Gehry building that opened about 1.5 years ago in Miami Beach in Florida. And it's a concert hall. It's basically a miniature version of the Disney Concert Hall in Los Angeles. And so it's a piece of architecture, a notable piece of architecture, where what happens inside is the creation of extraordinary music. And so the commission was to combine the history of music with the architecture of the site and the building. And so we started by taking photographs over a period of years, photographs of the building construction, photographs of the Art Deco neighborhood. And then from there, we started picking out elements that we thought had potential. For example, this one. And then we started to make compositions by hand. So in this case, we worked for about 1 year before touching a line of code. We built over 1,000 different compositions, and then we gradually narrowed that down to about 400 or so. And in the end, we had 365 different compositions that run on the building, one for each hour. So we started breaking things down into contact sheets, making decisions, sort of weeding out what we wanted to be there. And the reason that all of this worked, we were able to make 365 compositions that sort of last continuously, was because we used a little bit of randomness and a lot of sort of decision-making based on how we wanted things to feel. So we developed this really simple data system where we were able to tailor or customize sort of how much we wanted to leave to chance. For example, this says that it can scale between 0.25 and 0.75 over the original image file. This says that it can have a minimum angle of 0 to 360. So basically, we were able to really control and have a lot of decision-making over the amount of randomness that we brought into the piece. So after that, we built a series of printed images. So taking the static piece that's meant to run continuously and turning it into a series of still images. And so composition became far more important. And we used randomness, in this case, as a jumping off point. So I'll show you a few examples of the final prints here. Again, each one of these is based on one image of the neighborhood or the building in construction. And then, so this one I'm going to show you in more detail. I'm going to show you some of the process behind it, where we were just simply like rolling a die and sort of putting the images wherever they wanted to be with the constraint that they had to be at 90-degree angles. And so these are things that emerged, in a way, triggered the final composition. We left this one open to a lot of decision-making on our part. And so in the end, after we ran through a few hundred of these, we found a few things we thought were working, the way certain images would merge together, basically getting outside of our preconceptions of what was correct or what we could do and trying to open it up to things outside of ourselves. And then again, this is the final image where we actually constructed it sort of tediously, piece by piece, and made modifications in order to, in our sense, have it work. All right, so chance and art. This is an extremely deep topic. I'm going to show you some things that I know that you're aware of, but hopefully have this like narrow point of view on it that makes it a unique viewing of some of these pieces. And we're going to go shallow. So here we have Jean Arp. This is around 1916. And basically in this piece, after hundreds of years of artists doing precise, rational structuring of things, he opened it up to unexpected events. And so he has these pieces of paper which he dropped and then left them there. So now this doesn't seem like a radical gesture, but at the time it was a very radical gesture, largely responding to the chaos and destruction of the ordered society that produced the devastation of World War I. So here's a quote from Arp. Dada wished to destroy the reasonable frauds of men and recover the natural and reasonable order. Dada wished to replace the logical nonsense of men today with illogical nonsense. Marcel Duchamp, this was made a few years prior. This is a piece called 3 Standard Stoppages. He made them by taking a 1 meter long piece of string and dropping it onto the ground from 1 meter above the ground, basically marking where it landed, and then cut these wood pieces from where the string landed. So this was a critique, again, of structured order. It's more of a Dada gesture. And the idea is, why do I need to heed the metric system? Why do I need to sort of live within that construct? I want to make my own reality, my own world. I think what's interesting that Duchamp did was he used that as a tool. So this is called a network of stoppages. And he started constructing his own reality from these tools that were in a way, grew from chance operations. In what's oftentimes considered Duchamp's masterwork, the large glass, you see the stoppages here behind the bachelors as a part of this work. So he continued building on top of this, this structure that he built from chance. You really can't talk about chance in art without talking about John Cage. Although he was a visual artist, he's of course most known for his musical work. So I wanted to play you a little bit of this piece from Book of Changes so we can listen. There's a lot to be said about this, but essentially, music of changes based on the Chinese Book of Changes. Here, Cage used random chance operations to create these symbols and then use them to determine the duration and the pitch. I have a short quote from Cage. "Those involved with the compositions of experimental music find ways and means to remove themselves from the activity of the sounds they make. Some employ chance operations derived from sources as ancient as the Chinese Book of Changes, or as modern as the tables of random numbers, also used by physicists in research." So one reason that he did that, to quote again from Another Time, Another Place for Cage, "This means that each performance of such a piece of music is unique, as interesting to its composer as to others listening." So basically trying to open himself up to things that are outside of his preconceived notions of what sound and music can be. Another artist here we have Jean Tinguely. So Tinguely says, "To me, art is a form of manifest revolt, total and complete. With Dada, I also want to have in common a certain mistrust towards power. We don't like authority, we don't like power." So machines post-World War II were seen as instruments of the control of the state. And so in making this machine, this drawing machine, which is very disordered, very chaotic, he's building machines of a different nature. And simply drawing, which is something that's so personal, so controlled, he's saying and sort of leaving it open to these things that he's making. His most famous piece is Homage to New York, which is a massive sculpture that destroys itself over the course of a performance. This one was supposed to destroy itself, but kind of halfway through the performance, it caught on fire. The fire marshal had to come in and shut the whole thing down. I think this idea of a sculpture that destroys itself, it obviously comes from the atomic age. We've unleashed this awesome power into the world. How can we react to that other than to sort of embrace that destruction and this awesome force and build things that reflect that in the world? Of a different type, we have Ellsworth Kelly. In the early 1950s, he was living in Paris at the time. He started developing these idiosyncratic mathematical formulas for assigning color within a grid. Another piece of his is basically to make an image and then cut it up and then reassemble it according to this order that he set. Gerhard Richter. I don't have much to say about Richter, other than, of course, he's one of the eminent painters of the 20th century. But I have this quote that for me is really, really special. He says, "Above all, it's never a blind chance. It's a chance that is always planned, but also always surprising. And I need it in order to carry on, in order to eradicate my mistakes, to destroy what I've worked out wrong, to introduce something different and disruptive. I'm often astonished to find how much better chance is than I am." More works by Richter. Then the newest piece we have here is by Keith Tyson. This is from 2008. And so these sculptures were produced entirely according to the roll of a die. The first roll, numbers 1 through 6, sets which color will be on which face. The second roll sets the area within where something will be extruded or put inside. The third roll sets the amount of the extrusion, et cetera, et cetera, et cetera. You do a second generation. So basically, he sent an algorithm to the gallery, which was then fabricated. All right, order in art, the converse. We're not going to talk about this very much at all, but just to introduce it as the opposite. This is the work of Carl Andre, the work of Agnes Martin. And I recently came across this article by Rosalind Krauss that's a scathing review of this work within 20th century art, and I've come to really adore it. So I'm going to read a little bit of that. "It's not just the sheer number of careers that have been devoted to the exploration of the grid that is impressive, but the fact that never could exploration have chosen a less fertile ground. The grid declares the space of art to be at once autonomous and autotelic." So if you go into any museum in the country, I actually haven't been to this room in the Walker yet, so I'm excited to see that later today. You see something like this. This extreme exploration of this really narrow area. And Krauss, one reason that she's so against it is because she sees it as a moving away from humanity, a moving away from narrative, and basically making art of its own rather than a part of our larger intellectual and social discourse. But of course it didn't start that way. So here we have Malevich. He invented his area of suprematism in 1915. So here's an El Lissitzky quote about this. "We see that suprematism is swept away from the plane of illusion in two-dimensional planimetric space, the illusions of three-dimensional perspective, and has created the ultimate illusion of irrational space, with its infinite extensibility into the background and foreground." And Malevich says, it's meant to be the supremacy of pure feeling or perception in the pictorial arts. It's another work from the same time. And then this is an early work by Mondrian, who I think sort of in our general culture is most associated with this idea of the rational in the work. But in fact, he was highly idiosyncratic and highly emotional in how he approached the work. He started off, as many people do, in pure representation, moving a little bit more into abstraction, more into total abstraction, and then the work that we all know here. So when Mondrian did this work, he was thinking about the style of music that was emerging in New York at the time, which is boogie woogie. And the most famous piece from this time is Broadway boogie woogie, which this is not that work, but it's similar. So I want to play a little bit of boogie woogie for you. So you can see it fit. At least I can. When you look at Mondrian's work up close, this is his signature, PM. You can see that this is anything but highly refined. There's a lot of still emotion and humane quality in the brushstrokes. It's very different from what happened post World War II, when art really did become about the automatic, when people started fabricating things rather than producing them themselves. And so I think this early history of abstraction is one that's highly emotional, highly spiritual in the sense of not of the body, rather than the other sense. And so I think it's important to keep that in mind. All right, chance and code. So I think Kevin showed this yesterday, but it's extraordinary, so I'm really happy to show it again. 1 million random digits with 100,000 normal deviates. So the Rand Corporation, huge military contractor, they needed a large table of random numbers in order to complete their simulations. So we have an introduction, we have the methodology, and then we have the million random digits. Page 1, page 2 and 3, 4 and 5, 6 and 7, 8 and 9, 399, and 400. So the last digits, and then it begins the 100,000 normal deviants. So this work, why did they need to do this? So I have a quick quote from them. The Table of Random Numbers is the book that has become standard reference in engineering and econometrics textbooks that have been widely used in gaming and simulations that employ Monte Carlo trials. Still the largest known source of random digits and normal deviates, the work is routinely used by statisticians, physicists, poll takers, market analysts, lottery administrators, and quality control engineers. So basically, when you're doing simulation, the world is infinitely complex. Of course, computers now, and especially at that time, could not simulate every variable. And so you bring in noise in order to improve the quality of your simulations. And so at this time, Rand needed to produce this document because they were doing simulations of the complexity that the prior random number tables didn't extend to. And so the idea that they would have to go through multiple random number tables, which would then potentially cause a flaw in their simulation, or not as sort of high resolution of simulation. And so they built this table. But within digital computation, more of our nature and the sort of creativity, A. Michael Knoll was really a pioneer here. So here's a quote from Knoll about randomness. "The computer is a unique device for the arts since it can function solely as an obedient tool with vast capabilities for controlling complicated and involved processes. But then again, full exploitation of those unique talents for controlled randomness and detailed algorithms could result in an entirely new medium, a creative artistic medium." So in 1962, Knoll wrote a memo at Bell Labs, which of course at that time was really the dominant technology lab in this country, doing, in my opinion, the most interesting work. And it's called Patterns by 7090, referring to the IBM 7090 digital computer. And so he describes these different patterns that he creates. The straight lines in pattern 1 were created by connecting a series of points. Random numbers, standard deviation of 1200 were used for the x-axis coordinates, et cetera. This is the Fortran program that he wrote to produce these images, and this is the image. We still see images like this thrown up on the web by undergraduate students, et cetera. In many ways, we've progressed very little in 40 years. But at the time, this is a really exciting image. Computers were not powerful at the time. I think employing randomness allowed you to sort of get more from them or to do unexpected things. This idea of using a rational machine to do something unexpected, I think, at that time was a really subversive one. Here's another image by Frieder Nake. This one's from 1965. 1965 was the year that the very first computer graphics were shown in galleries. There was a show in New York. There was a show in Stuttgart. Knoll was in the New York show. Nake was in the Stuttgart show. This piece, I think you can see, if you code, you know the algorithm here. Basically, random numbers were chosen. The density, the pin. So for example, this was done on a plotter. So to change the pin, you actually put a red pin in or put a black pin in. And then also the location were chosen by random values as well. But of course, random values weren't used exclusively for military contractors. For example, the RAND book, in random research, was largely funded by the military. It was used for the burgeoning hobby community as well. So this is the People Computer Company's 1972 guide to using BASIC. So here we sort of learn about BASIC in, I don't know, I love this, I adore this. But also within this really short book, we also learned about random numbers. So early on, random numbers were essential to this idea of entertaining or hobby computing. Here, for example, it shows you what a random number is using a coin flip, using a die. And then here's the basic program that allows you to explore it in this way. In 1982, the Commodore 64 user manual, of course, introduces random graphics as well. And we're going to talk more about this program that you see here in a little bit. So demo. What I've done is I've collected a few demos that, in my opinion, that I've seen over the years that really highlight or show randomness in isolation so that we can really look at it and look at its effects. The first one's from Leah. This was from a book called 4x4 Generative Design that she was one author along with Golan Levin and a few other folks. So let's look at this. Here we have the perfect ordered grid. Here we have a deviation of 1 pixel. Here we have a deviation of 2 pixels, 4 pixels, 8, 16, and now we've basically deviated entirely from that original grid. So I think the question is, somewhere in between here is the space from order to chaos. Next one is from Jared Tarbell. Let's look at that slide first. This one's called Fractal Invaders. And this one uses a 5x5 grid. And what it's doing is, right now we're looking at a 3x5 grid, is on every time that it updates, it rolls a dice or flips a coin. And if it's heads, it's a white square. If it's the opposite, it's a black. So it's pure randomness. But if we use a little bit of symmetry, and we just copy over the left 2 columns on the right, then we start to see things. We start to see skulls. We start to see people. We start to see faces. So I think this is a really interesting example to show how you can have something that's totally ordered, but then you add a little bit of symmetry, this duplication, and suddenly it starts triggering our imaginations, and we start reading into these things, and these sort of base pattern recognition algorithms we have in our head get triggered. See, the next one we have is the algorithm that's behind some of the work that I showed earlier. This one is based on a piece called Articulate. So this is what it produces. And I'm going to build the algorithm up a little bit over time here. This is the first example. Here we're using randomness in 2 ways. 1, to set the size, and then 2, to set the location. But we have order, where when we move one over the other, they move away from the center point. Next, we add something. We add the ability for them to move on a straight line, but then when they overlap with another, they begin to rotate around. Next, we take something away and add something else. Now we're adding a line between the center points of the circles when they overlap, and then remove the circumference. And so that leads to this piece, which is the origins of quite a few things that I've done, where I can cause them to grow from different areas. For example, the top and bottom of the screen, this is an even sort of maximum entropy distribution. Here, they start at the circumference of a circle, here from a line in the center of the screen. So we have something that's emergent. It's totally moving from the bottom up according to the instructions of these individual elements. But by ordering the initial condition, I'm able to sort of coax them or have them grow in different ways. So I think it's a really nice balance between this emergence, a little bit of chaos, and a lot of structure as well. And this can be visualized in a different way that gives a different read to it as well. For example, now we're just looking at the yellow dots we were seeing before, and it's drawing over itself. So here's from the circle. Here's from the center point. Here's from the top and bottom. This one does something interesting when they meet in the middle. And here's the even distribution. So the last one to talk about is this one-line Commodore 64 program, which I talked a little bit last year at I/O, but I've actually spent the last year with 9 other people writing a book around it. And so it's been in my mind, in my memory, and we've moved much further with it. So let's look at some of those demos. I think this one particularly shows, maybe in the most basic way, how this randomness works. So we're going to start by writing out the basic program. We'll do 10 print. That prints to the screen. This prints a character. This prints character 205, which is a, oh, you know what? I need to show you some other things first. This is a Commodore 64. And what's interesting, one of the many things interesting about the Commodore 64 is that it has these graphics on the sides of the keys. And the two graphics we're interested in here are this diagonal and that diagonal. And this is character 205. This is character 206. And this is a, the system here is called PETSCII, which is similar to ASCII but developed for the Commodore PET. This is the page of the user guide that shows the way the numbers relate to the images. All right, so back to here. 205 is one diagonal, 206 is the other. So we're going to give it that, and we're going to say plus a random number between 0 and 1. And then we're going to put a semicolon there, which means the characters print one after another. We're going to put a colon in there, which means that I can include 2 lines of code on one line. Then I'm going to say go to 10, which just runs it after itself. Then I'm going to say run. And we see the program unfold here. I think what fascinates us about this program is it's simply just flipping a coin and then drawing a left or right. But it creates this pattern where we have open areas, we have closed areas. It becomes vaguely maze-like. And we're able to approach computing from many different angles just using this single program. So I want to build up to it. So we're going to start off by just drawing character 205. This is the pure order. This is character 206. So another example of pure structure. This one is one character directly after another. So we have a little bit more variation, but still total structure. And then, now that we've done that, let's look at the original program again. You can get a better sense of how it's operating. And we can do other things with it. We can unbalance it. We can, for example, weight the coin so that it's tails 9 times in a row and rarely comes up with heads. And that begins to create images that look like this. We can, every number is associated to a character, so we can try different characters and see how that affects it. So this is the same system, flipping coins, drawing one or the other, but because we're using different characters, it creates a different kind of feeling, a different kind of mood. We have different kinds of associations with it. So the question is, how is that different from the other, when essentially it's the same algorithm? Here's the last one I'll show. This one is just using two different characters, 181 and 184, but because they're not adjacent to each other, we have to write a little bit more code, multiply by 3 there. So I think what's interesting in looking back on things like this is it gets us to think about our assumptions about how computing works and how software works and how it's essentially tied to different hardware platforms. So this is the equivalent in processing. This is a one-line program, and it doesn't do anything at all similar. Basically, what I mean by similar, it's a similar algorithm, but of course does something totally different. We have to do it into the console. We have to use the slashes instead of the proper characters, but this is sort of how you approximate that in processing. If you want to approximate it in a different way, you have to go down a different route. No, I don't want to exit that. All right, so a little bit of current work, and then we'll wrap it up. So as I said, we've been working on this book now for over 2.5 years, and it's finally finishing up. This is the list of extraordinary authors that I'm really lucky to work with, and this is a variation of the 10-print algorithm. And so one of the things that I did on the book was to explore this algorithm outside of the hardware, the platform of the Commodore 64, and to see what I could do with it in a different environment. And so the very first thing that I did was not really very interesting, but I want to show you the process, was to just implement it inside of processing. And you can see one major difference here is that the entire thing's updating rather than one piece at a time, which is really a radical difference. I can, of course, weight the random value here. For example, this is 95% going to turn up on one or the other. Line thickness is something you don't have control of in the Commodore 64, but it's interesting to see how that affects the perception. of things. And of course, I can modify the frame rate. Commodore 64 kind of runs at 1 speed. Here we can try different areas. And then, of course, modifying it to different graphics. And sort of seeing, here we're just treating pixels, black or white, how the character itself affects our perception of this system, dots, and then the binary. All right, so from there, I increased sort of the quantity of randomness in the piece. So let's look at that. This was a piece done for Written Images, which was a publication that came out last year that many people in the room contributed to. And here, what we're doing is allowing ourselves to use different colors. We're using white for one direction, black for the other. And we're also able to randomly select the number of rows we want to have and the weight of the line. And so what we're doing here is every second we're going through and selecting a different parameter space. So the question is, like, how does it depart from the original Commodore 64 algorithm? What's the difference? What's unique to these new systems versus the prior ones? And here's the last iteration of that, where even more randomness has been introduced. So I think it gives you the quality of like how far to push it or how far to constrain it. And so here, the only difference is that also the line thickness of each line is selected by random too. So for me, this is the right balance of structure and sort of unexpected juxtapositions according to random values. All right, the last thing to show is this piece called Century. And this piece right now is a work in progress. And the goal of the piece is to go through 100 years of visual arts and to pick specific artists and specific series of works and specific paintings and to sort of expose the underlying algorithms and to compress that into one piece of work where we can sort of understand the innovation that happened during this last century and also have the sort of the underlying systems be revealed through randomness and through parameterization. So let's look at this a little bit. And I'm helped with this project by Scott Murray, who's here at Eyeo. Thank you very much, Scott. Let's check this out. So right now it's at 9, and I'm going for 100. So we're going to see the current status of things. And I'm just going to flip through them first. So in one sense, it's incredibly underwhelming. Like, the graphics are really simple, minimal, primitive. But for me, that allows us to look closer and encourages you to look closer. And that's my goal in this piece. So let's talk about them. This one's Ellsworth Kelly. We saw a similar piece earlier. And so the interaction on this one basically allows you to expose the system that he underwent to do the final piece. So anytime you click, you're able to freeze and then modify. This one, Saul LeWitt, it's selecting on each grid unit between 4 different options, 4 different variations. And so through interaction, we're able to then basically reformat one of the rows. This one, Vera Molnar and her husband, Francois. This one's the most similar to 10print. It's actually almost identical to 10print. And here, through the interaction, we're able to flip them around. It just uses 2 different characters. This one, of course, Bridget Riley. Here, we're able to control the resolution and then also the scaling, but then also the left to right. And then every time it sort of regenerates itself, it sort of picks a different gradient in order to diffuse some of the dots. This one, of course, is Malevich. It's actually based on the genesis of this entire project was a piece done by Jean Tanguy called the Meta Malevich, where he basically produced these lines, hooked them up to motors, and then had them rotating. So this idea of making a Malevich that sort of builds on that painting, and the idea of this in software is to build even further. So when you select this one, you have this ability to move around. So each one of these is algorithmically not interesting, but the idea of the sum of the whole and looking at this 100-year period and being able to expose the system over that entire period and sort of the mass of the piece for me is what's engaging and interesting. So through this exploration of randomness over the last decade, and then specifically now really honing in on it, and essentially, you know, like Rosalind Krauss, I'm really skeptical of this work, but at the same time, I really adore it. And so I'm basically trying to go really deep and to try and emerge from the other side with some other kind of knowledge and then to share that. I should also say about this piece, it's the first piece that I've ever done that's meant to live and operate within the browser. And so it will be doing that. It's also really custom coded to work at multiple scales and sizes. So with that, I'll end, and thank you very, very much.